Okay, so today we are going to continue our conversation from Thursday of last week. Thursday we discussed rates of change, and we introduced the concept of function notation and how we can use it in rates of change, but we didn't get a chance to finish that discussion and get some good practice. So today we're going to have a refresher on what function notation is, and then we're going to take a look at how to solve rates of change problems using this new notation. So we are used to seeing equations with an x input and a y output. That's something that we're used to seeing. Excuse my poor handwriting on this. So an x input and a y output. But now that we're using function notation, we're still going to be using an x input. That hasn't changed. But instead of calling our output y, even though it's still measured on the y-axis, we're going to use f of x to describe our output. So this is going to be our range. It's going to come from the outputs of our equation. We're just going to call it f of x. And the reason this is helpful is because the x that we've plugged in is technically still part of our equation here. It's still inside this equation. It's just inside the notation. So I can see exactly what I plugged in and exactly what has come out in at the same time. This notation can be helpful because it can make solving different types of problems much less confusing because we can use the same method every single time. So let's go ahead and take a look at some rates of change problems and how to use function notation in order to solve them. So if you already had a chance to write the coordinate notation and the function notation side by side in your notes, you don't have to write it over again. But if we didn't have a chance to get to this point, go ahead and copy this down in your notes. So we're going to take a look at coordinate notation. This is something that we've used before. This is what we're used to. It's where they give us coordinate pairs or a graph where we can find coordinate pairs. So let's say an x1 and y1. And then they give us another set. We can call those x2 and y2. So our first input and our second output, first input and our first output, and our second input and our second output. And we can use those to find a rate of change by using the formula that we're used to, y2 minus y1 over x2 minus x1. So this is something that we're used to. And we're going to take a look at how to write this exact same formula with our new notation. So with function notation, typically they won't give us sets of coordinate pairs. What they will do is they'll tell us an interval. Remember, intervals are always just x values. So they'll say we have a starting x value, and they'll call it the letter a. And then we'll have an ending x value, and we'll call that the letter b. Now, intervals are always x values unless we say differently. So this a, this first input, this first x value, is the exact same number as our x1 would have been. And b, which is our second input, is the exact same number as x2 would have been. So if we wanted to use coordinate notation to write our interval, we would have x1, x2, and that would be the same type of interval. But in this case, we're using our function notation. So with function notation, we want to write our fraction, just like we did before with rates of change. And on the bottom of our fraction, just like we had x2 minus x1, we're going to have b minus a. B minus a. So our second input minus our first input. That's going to give us the change in horizontal distance, which we call the run. Remember, our slope is the rise over the run, so we also need to have the difference between our outputs in the top of our fraction. We had been calling those y2 and y1, but in this case we're using function notation. So where we had an input of x2, we had an output of y2 right on top of it. Those were our coordinate pair, x2 and y2. So in this case, if I'm plugging in b, the output that's associated with that would go right over top. And we know with our function notation, if I plug in b, my output is called f of b, whatever that output may be. And then likewise, if I plug in a to my function, I will get f of a as a result. And you can see that they're right over top of each other, and this is a much more simplified version of this equation. And let's go ahead and see if we can use this to solve some rates of change problems. So the first rate of change problem I want to look look at with you has coordinate pairs in it. So they've given us two sets of coordinate pairs, and we would be used to calling these x1 and y1 and x2 and y2, but we don't necessarily need to do that anymore. The first step, the first thing that we should do is to go ahead and write our interval from our problem. And again, for our interval, we're looking for x values. The very first x value I can plug in, the furthest to the left, and then the x value I can plug in that's furthest to the right. So I have two x values in my equation down here in my coordinate pairs. I have a 1 and I have a 4. So the 1 is furthest to the left and the 4 is furthest to the right. So that's how I would write them inside my interval, 1, 4. The next step is to go ahead and take a look at our function notation formula for rate of change, f of b minus f of a over b minus a, and turn that into a fraction with these actual values inside of it. So we know that the first x value in our interval is our a value, and the second one is b. So we can go ahead and plug those into the bottom of this fraction really easily. That's always going to be our easiest part, is just plugging in our b minus a. Now we have to take a look at what our outcome is going to be. So I know if I plug in b, I get out f of b. So if I plug in 4, I'm going to get out f of 4. And over here, if I plug in 1, I'm going to get out f of 1. And in our next step, we're going to go ahead and take a look at what those outputs are based on our coordinate pairs. So if I say that I'm plugging in 4 and getting out f of 4, that's actually where I'm looking at my coordinate pair and saying, okay, if I plug in 4, what do I get out? And I get out the number 7. So this f of 4 is going to turn into the number 7 in my formula. And then if I plug in the number 1, I'm going to get out the number 3. So my f of 1 is going to turn into the number 3. That's what I get out of my coordinate pair. And the bottom is still 4 minus 1. Now in my last step here, very last step, all I have to do is simplify this equation. So this is going to be step 4. We will simplify. So 7 minus 3 is just 4. And on the bottom, 4 minus 1 is 3. And my answer is a fraction. And that's actually fine here because rate of change means the same thing as slope. And we know how useful fractions are when we're using slopes in mathematics. So if we're trying to use a slope to graph something, having a fraction as a slope is really, really helpful. Now we did take these fractions and turn them into decimals or whole numbers in some of the examples we did, which are really, really helpful for using context. So if we're trying to find context, we want to simplify this fraction and actually type it into a calculator. But because we have no context, a fraction is fine, okay? Let's take a look at one more example together. In this next example, we are given a very poorly drawn graph. Sorry about that. And we want to find the rate of change of this function between 1 and 3. So that's our first clue there, x equals 1 and x equals 3. Remember, the very first thing that I want to do is write an interval. So we're going from 1 to 3. Oops, and that should be parentheses. Shouldn't be parentheses. Sorry about that. So we're going from 1 to 3. There we go. All right, so we have our interval. Now we want to go ahead and take a look at our formula. We know it's f of b minus f of a over b minus a. And we know that the first x value is a and the second x value is b. So we can go ahead and fill in part of this fraction with values right from our equation. So we have on our bottom b minus a, 3 minus 1. For our top, we have to find f of 3, and we have to find f of 1. And that's where we're going to look at our fraction. Sorry, not our fraction. We're going to look at our graph. So if I know my input is 3, that's this 3 right here in the bottom of my graph under the x-axis. In order to find my output, f of 3, remember f of x is the same thing as y, so this y-axis is actually my f of x axis. So in order to find my output from 3, I need to go up and see how far I go on my f of x axis. So if I'm going to go over 3, I need to go up 50 in order to get my answer, in order to meet the graph. So this f of 3 is actually going to become the number 50. And the same thing's going to happen when I plug in f of 1. If I go to 1, in order to find what f of 1 is, I need to go up until I meet my graph. And I'm going to go up a total of 25 units. So my f of 1 is going to be the number 25. And then on the bottom, we have 3 minus 1. And we need to simplify this to get our answer. So our last step here is going to be to get our answer. And our answer is going to be 50 minus 25, which is 25. And 3 minus 1, which is 2. Sorry about that. Oops, it's going to keep doing it. There we go, 2. So our final solution is going to be 25 over 2. So what I'd like you to do now is take a look at the next 2 examples. I have a way to use rate of change is given a table. So go ahead and copy this table down into your notes and try to use the rate of change formula we just discussed, f of b minus f of a over b minus a, and try to see if you can find the rate of change between -1 and 5 using this table. And then, after you finish that, go ahead and copy down this equation into your notes and see if you can find the rate of change between 2 and 4 using function notation. Once you're finished those 2 things, please raise your hand so I can come check your work or answer any questions you've got. And once I see that you're on the right track, I'll give you the link to the next video that I want you to watch, starting our unit on functions. So you can go ahead and get started with, with our function transformations. So you can get started on that one, okay? All right, go for it.